Hello. So I'm Francis. I'm going to talk today about a project I worked on last year called Policy Space, um, in particular, the transit demand model part of it. So just a little bit about my background. I mostly work in simulation and machine learning. These are a few projects that I've worked on in the past. I've worked on things around drug discovery, automated drug discovery using machine learning to sort of hack around patent law, urban simulations more generally. This project over here is about computer vision. It's a conspiracy generator, basically, that uses how computer vision misidentify stuff to generate conspiracies. But this particular project is called Policy Space. I worked with this researcher, Bernardo Alves Furtado, at the Institute for Applied Economic Research in Brazil. He's been working on economic simulation for many years now, and this is sort of his big project. The idea basically is that we take Brazil and its municipalities and we simulate labor, housing, and goods markets and tax schemes for all 46 of these metropolitan regions. So we model things like how firms hire and fire people, how people find jobs, how people decide on where to move, how people decide on buying or selling houses, and so on. And the output is a lot of graphs like this. So this is pretty typical, comparing different outcomes for different starting parameters, which can be related to tax amounts or various other things like that. So there is a spatial component to the model because we consider, if a person has to decide on where to work, they may make the decision based on how far they are from their potential place of employment and so on. But we wanted to expand a little bit further because we just had this really, really naive kind of sense of space in the model. So we wanted to see how, changes in employment or changes in taxes and so on might affect different demands on transit. Okay, so the core kind of problem we were trying to solve with this, at least this initial simulation, was just basically modeling how people get from point A to point B. So if they drive, what roads are they taking? If they take public transit, what uh, what are the details of those trips and so on? Okay, and so instead of doing all of Brazil all at once, we first focused on Belo Horizonte, which is, I believe, the sixth largest city in Brazil. It has a population of about 5.1 million. And crucially for us, it had OpenStreetMap data available for it, as well as GTFS data, which was sort of the baseline necessary to actually do this kind of modeling. So we could have a map to work with and also know the timetables for all the public transit. So just a quick overview of how we built it. We used this simulation method called agent-based simulation, which I'll explain a little bit more about. And specifically, we used a discrete event simulation as well. We make a lot of really simplifying assumptions, especially for this first go at it. We treat roads as first in, first out queues. So basically, if you're the first to arrive on a road, you're going to be the first to exit it as well. So that basically means that no cars pass each other on the roads. We treat space as continuous, so a lot of times you'll see like space broken up into zones with this kind of transit modeling, but we don't do any of that. We only consider work commutes. So again, the model, a lot of it's focused on employment, people going to and from work, and so on. So that's all that we're modeling to start with. We exclude these events such as accidents and so on that may be kind of exceptions to traffic, to regular traffic. And then we model both public and private transit. So I won't have too much time to get into the details on the routing, but for private transit routing, we use an algorithm called A*, which is a really common pathfinding algorithm. It's used in video games a lot. And then for public transit routing, we use an algorithm called connection scan. I think it's just connection scan algorithm. And I'll talk a little bit about that. But first, I'll talk about what agent-based modeling is. So this is sort of one of my favorite examples for where this comes into use. So this is a swarm of, or various swarms of birds flocking. And it's a really, really highly organized behavior, but there's no general bird directing all the other birds on how to do this. Each bird this is sort of an emergent property of the individual decisions of all these different birds. So how would you model something like this? So one way is this algorithm called Boyd's by, I think initially by Craig Reynolds. Um, and you can see these little triangles are little birds, and the flocking behavior is pretty similar to what we just saw. And this is a basic example of agent-based modeling. So the basic idea of agent-based modeling is that you just create a set of rules for each individual entity agent in the system, and they make these rules are usually very, very simple, and then they all make decisions based on these rules, and then the ordered aggregate behavior comes out of an emergence of these simple actions interacting. So in the case of Boyd's, the birds or the Boyds have three simple rules. One is that they try to avoid colliding into each other. Two is that they kind of try and steer themselves to the average alignment of nearby Boyds. And then sort of in tension with them trying to avoid colliding with each other, they also try to move towards each other. So there's kind of this ebb and flow there. And from these three simple rules, we get this kind of pretty remarkable ordered behavior. So that's the general principle of agent-based modeling. For policy space and for this transit simulation, we just do the same thing, except we have people in cars or people going to and from work. And then discrete event simulation. So when you do these kind of simulations, you often have to figure out how are you going to model time. You can model time continuously, which can be kind of tricky, or you can kind of break it up into only look at events that are relevant that are happening. So here we basically have our set of agents on the, I guess, on your left, and then we have a queue for events. Oops. Oh yeah. And basically, anytime something significant happens, like an agent gets to a place or is about to leave for a place or something, we take that event and we just stick it on this event queue. Oops. And that's always sorted by time. So we always process the things that are happening sooner first. And then we just kind of go down the list. And as agents, arrive to their destination or have to make a transfer, something like that, we just plop those onto this queue and we just kind of process that through. Okay, so that's like the super high level basics of how the simulation works. As you might expect, there were a lot of challenges in building this prototype. The first is just running a simulation with 5.1 million agents in it. In policy space, that's for all of Brazil. We run with like 0.01% of Brazil's total population. Here, I think maybe when we were developing it, ran with like 1% of Belo Horizonte's population, and it was slow. Like it took, God, like 16 hours or something to do one run or something like that to start. And a lot of it was slow because of these because of the routing algorithms. So I had to spend a ton of time just experimenting with different ones. I kind of stupidly tried implementing my own from scratch. Did not work. And then eventually settled on this one, which I believe is the one that Google uses for Google Maps routing. But that was a kind of really grindy problem. This particular problem was one of the more interesting ones that came up. So we have GTFS data, which tells us all the bus stops in Belo Horizonte. And that tells you the latitude and longitude of these bus stops. And it has a road name that bus stop is associated with. It, however, does not tell you along where that bus stop is. And since we were interested in modeling buses as part of the regular road traffic, we had to know like exactly where along this road this bus departs from or picks people up from. So we basically had to, given a coordinate and a road name, figure out where along that road that bus stop actually is. So I broke it down into this sort of dummy road network to just try and solve the problem. And then I figured that, okay, each of these roads, there's a bounding box associated with them. So a box that encloses the entire road with some padding. And what I decided to do was take these bounding boxes and index them in this data structure that's called a quad tree. If you've ever worked with like a KD tree, it's similar, but basically it makes it so that you can take a point and then search through a bunch of bounding rectangles like this, and it'll return the ones that overlap with that point. Right. So given a bus stop, let's say this is the coordinates for the bus stop. This quad tree will tell us, we give it a little padding radius as well. This quad tree will tell us which roads actually overlap, which bounding boxes overlap with that one. Right? And then all we have to do is take this query point, this bus stop coordinate, and just figure out what the closest actual road is and what the closest point is. So we just take, was it a projection of this point onto there, and whichever one is the shortest, that's the best candidate. So that gives us the closest point, and then basically that's how we figure out where along that road that is. So in this image here, the blue point is the bus stop coordinate, the green point is the best guess, and the yellow are the other guesses. So it seems to work pretty well, but of course, there are a lot of situations like this where the bus stop coordinate is smack in the middle of two roads, which kind of sucks, but here it's not too bad. What we can do is we can take the road names and just disambiguate it that way. So that problem was solved pretty much. But then another problem came up. So as I was saying, we wanted buses to travel the same roads as private transit. So we could model like if a road gets clogged up, then that's going to affect bus arrival times and departure times and so on. But often when we sort of unleash the buses onto our road network, it could not find a path between certain bus stops, which is really, really weird. So this took a really, really long time to figure out. I had to produce like tons and tons of these maps and like go through them by hand to figure out like where the routing was going wrong. It was a huge pain. And so then I would come across cases like this. This is like one of the simplest ones. So this is the bus stop here. This is where the algorithm I just showed you figured where the bus stop actually is on the road. And then this bus, this is a one-way street, is just trying to get somewhere, but it can't because this one-way street dead ends right there. So that's weird. Why would they plan a bus route like that? Well, it turns out if you look at Google Maps, this is actually a complete road. But for some reason, that crucial bit is missing in the OpenStreetMap data. So yeah, so I spent like, weeks probably looking through this until I just realized, oh, it's just the data quality is not good. So that sucked. So then finally, when I revisited this project a couple months later, I was trying to calibrate all the transit times so that buses would arrive roughly on schedule and so on. And I could not figure out why this one agent was trying to take this bus trip. And if they traveled by private car, it took like 30 minutes or something. If they traveled by bus, it took like 5 hours or something like that. And I thought something was just wrong with the routing, like maybe some more data was missing, or I just coded some of the bus travel speeds wrong or something like that. I spent like another week on this, and then I just realized, and I just punched it into Google Maps just to check my work, and it just turns out that it's that much slower. And so yeah, I don't know. Thank God for Google Maps, I guess, because it lets me check my work like that. Anyways, so it was a really interesting experience building this simulation. This is the first time I'd ever done a transit simulation. I learned a lot. And I think the most crucial lesson I learned is that the quality of it is entirely contingent on the available data and the quality of that data. So the GTFS data, the coordinates weren't super accurate, so I had to spend a lot of time adjusting for that. And then just like missing OpenStreetMap data, it was kind of rough. It's a great resource, but you do have to just kind of keep that in mind when you're working with it. And I didn't really get into this part of it too much here, but obviously a simulation of everyone in a large city can quickly get very, very complex. And it just made debugging things really, really difficult too. So yeah, thank you.